Hi everyone. If you're like me, you're trying to be more active. And one way to be more active is through the use of active transportation, like walking, biking, and cycling, and wheeling. But the key thing to facilitating this is having active transportation infrastructure. And that can mean a lot of things, but might be sidewalks, might be trails, might be bridges. But one of the challenges facing small cities is the ability to predict the demand for such infrastructure. So, what I'd like to do right now is take you through some research we've been working on that speaks to a case right here in Fredericton using a method called a four-step model to try and predict how many people might use active transportation and the benefit of using that tool to try to help understand demand. This is a presentation that I gave on behalf of Kristen Burns, one of my former master's students, just graduated, and myself at the Canadian Transportation Research Forum. This presentation is called A Tale of Two Bridges, using the four-step model to understand active transportation usage across the Wolastoq, St. John River, and Fredericton, New Brunswick. Where did this research come from? It came from the fact that I think we know that there's a pretty big difference between the two bridges in downtown Fredericton, the Westmoreland Street Bridge and the Bill Thorpe Walking Bridge. Two very different experiences. And I think what we wanted to accomplish was using a traditional type of approach to understanding travel demand, something that's been used since the 1960s, but primarily for vehicle counts. Could we use something like this to help us understand something about how active transportation is used in Fredericton? And then by virtue of doing that, whether it's the potential exists for using this kind of older approach to solve these kind of problems. What many people probably don't realize is that there are some challenges facing transportation planners in small cities. In particular, is that when it comes to the use of active transportation, it's really challenging to try and predict demand. What you'll tend to see is plans where the automobile component of the plan is pretty sophisticated. You can estimate volumes quite close to reality and can get really good numbers about delays, level of service, etc. But on the active transportation side, walking, biking, cycling, those plans tend to be more qualitative in the sense that we're probably going to want this kind of trail to connect here to here, kind of a connectivity kind of plan, or maybe we want to see a bike lane here, and it's based on more conceptual ideas of connectivity, but not a whole lot about how many people you would expect to use this infrastructure. And what we found by going through the research was that there really isn't a lot of standard guidance for active transportation demand modeling. So this is why it presented itself a really good opportunity for Kristen's thesis, was that let's take a method that has been used for decades, but only really used for understanding car travel behavior, and see if we can use it to understand active transportation use. And there's probably some pretty good reasons why we haven't done this. And part of that reason is that it usually requires a lot of data, and the difference between active transportation use and car use is pretty dramatic, like 100 to 1. And the tools that we use tend to be pretty good when you're dealing with big numbers and not very good dealing with small numbers. So we know that there's been increasing public pressure for another river crossing in Fredericton, and there are 3 bridges in Fredericton, but only 2 allow for walking or cycling. And so what we thought we could do here is see if we could use something called a four-step model. A four-step model relies on taking the city, breaking it up into squares or into shapes that align with how the census is reported. So these are called dissemination areas. Taking each of those areas, figuring out how many trips are generated there, And then where those trips go is a function of the type of attractions that trips might want to go to. A home-based work trip, for example, would probably want to go to a place where there's lots of jobs. What we're thinking is that even though the Westmoreland Street Bridge is a more direct route for pedestrians, it's not nearly as many people on it as you would expect when compared to the Bill Thorpe Bridge. So what we didn't know was that, are there fewer people because they don't like it? Are there fewer people because even though it might look like a more direct route, the population isn't there? It's actually closer to the Bill Thorpe Bridge. So either way, we thought, given that the 4-step model is not typically used in smaller cities, they typically use what's called a 3-step model. That is, they're really planning for car trips only and not for any other trips that can go by other modes. So our hypothesis was that users are paying some kind of cost penalty to the Westmoreland Street Bridge. What does that mean? Well, if both bridges were equal in terms of how people like them, you would assume that if the travel times were the same, then half the trips would go on one trip on one bridge and half the trips would go on the other, that people wouldn't have a preference for one over the other. We broke the city up into 54 dissemination areas and looked at 3 modes of transport: car, biking, and walking. And 3 trip types: home-based work, that's a trip from your home to where you work; home-based other, a trip from your home for some other purpose; and then non-home based. The difference being with each of those trips is that where trips are going to be attracted to will be a function of what is in that other zone. So if you've got like a zone that's, let's say this one right here, and you've got, let's say 500 trips of which 300 are home-based work, those trips are going to go to a place where there's going to be a lot of jobs. And so downtown tends to have a lot of jobs. So maybe that there's a proportion of these trips that go downtown, a proportion that go to Main Street, a proportion that go over here. And our job as modelers is trying to figure that out. But if some are going here, then some are going to be crossing the river. And then the question is, well, what are those numbers going to be? You notice we didn't include transit here. And I really wish we could have. The thing is that, for one, at the time, we didn't have any numbers for transit. We didn't have any idea of how many people were taking the transit on a zone-by-zone basis. In addition, when compared to cars, bikes, and walking for going to work, transit is about 1% in the city of Fredericton. So we could have done a lot of work to put the model together, but it probably wouldn't have told us anything different by including those transit trips. I highly believe that we need a transit model for Fredericton, one that will allow us to determine what the impacts of making changes that would result in improved service for folks. And I'm hopeful we'll get there because I know the city is starting to collect data now. So where does one get data? Typically a place would want to do a survey, but the challenge was we wanted to do this from the ground up without doing any surveys. Let's see what data that we have access to, and can we build this from the ground up? So let's look at the volumes on the 2 bridges. You'll notice that in the Westmoreland Street Bridge in red here on the bottom, and the time of day on the x-axis. So 13 o'clock would be 1 o'clock, for example. You'll notice that it's almost 6-1, the Bill Thorpe Bridge compared to the Westmoreland Street Bridge, and also some peaking around 8 o'clock at night and during the meal times. But pretty dramatic difference between the 2 bridges in July. And these are, again, hourly volumes total for the month. So you divide by 31 to get the average daily values. So this would be like 6,000 people during the month walked around 1 o'clock. But if you compare this to January, you'll notice this is about 1/6 of what it is in the summertime. So pretty marked difference. But again, almost 7 to 8 to 1 between the Bill Thorpe and the Westmoreland Street Bridge. And the sound levels, the big difference, 74 decibels is really loud traffic. So then the first thing was, let's see if we could do everything we could possibly do, how close can we get to the numbers that are in reality? Then the second thing would be, let's calibrate everything, the Westmoreland Street Bridge, and see what numbers we get. And then finally, let's add in a new bridge. Let's have some fun and see what would happen to put a new bridge in. So the original calibration. In this case, we were able to get volumes on the Bill Thorpe Bridge to be almost identical to the average annual daily volumes for the Bill Thorpe Bridge. Pretty incredible. But you'll notice that we did a really good job getting the car volumes. We were pretty good on the biking, but the link volume for walking, we overestimated by well over 1,000 trips, average annual daily, on this bridge. And so what we see is that there should be about 1,000 more trips, walking trips on the Westmoreland Street Bridge than there are in reality. The perceptions are probably correct. It is theoretically a shorter way for people to go, but they're not using it to what we should expect. So then we said, well, what can we do to make this work? How do we make these volumes get close? Do the one thing that we could change, and that was the length of the bridge. Why would we change the length of the bridge? Well, again, people are paying some kind of penalty for that bridge. They don't like it. So we're trying to equate it to something that we could probably easily define. And what we did is I said, well, let's make the bridge longer to the point at which the volumes on the bridge for our model equate to what they are in reality. So this segment length here is about 500 meters. In our model, we kept increasing that length more and more, and until we got to about 2 kilometers. So what that meant was that in order for us to calibrate this, in order for the volumes to match what it is in reality, it's like people were thinking this bridge was 3 to 4 times longer than it actually is. That's the equivalent penalty that people are paying. So we decided, well, let's put in another bridge. We can do that. All it is matters of drawing a link. The hard part's building the model. And we know that the city has looked at this in the past, and it's quite expensive to do this, and I don't know if we even know if it's possible to do this on the piers. But a model, links are cheap, so that's what we did. So we put in this extra link, and what did we find? Well, because people who pay a penalty to use Westmoreland Street Bridge, everybody who was going there would go to this new link. And it also would draw from people that are now going a little bit longer over on the Bill Thorpe Bridge. But what did we find? You'd expect about, on average per day, 2,000 active transportation trips on average. Everybody that was on Westmoreland Street Bridge would go there, and it would take some from the other bridge. So that's suggesting that if they were to build a new link or to upgrade the bridge so that it was more attractive compared to the Bill Thorpe Bridge, that it would attract users. There are some limitations with our work. It's with this kind of work, we didn't include anything about recreation trips, though we did account for non-home based trips. And we're using journey to work data, and journey to work only covers really a small percentage of overall trip making, so it's not perfect. But given what we were able to determine with this, from what I can tell, it's one of the first applications, certainly in a small city sense, to see whether or not you could answer a kind of question with this particular model, that using this to determine whether active transportation link would attract users and reduce from automobile use. So from our model, it's basically people are looking like the bridge needs to be 3 to 4 times longer to AT users. And we ended up taking some numbers from Los Angeles, a very car-dependent city, and they seem to work for Fredericton. And I guess my final point is that there's a lot of value for small cities, that in this kind of case, that if you're trying to determine, right, the connection between active transportation use and driving, if you want to see whether or not people are going to make a decision to change for one over the other, a model like this helps you compare and can help you answer some questions about whether an AT infrastructure upgrade would result in some change. So now, I'd love to do more of this work. need to look at seasonal adjustment factors. We didn't include anything about sound and sidewalk widths, differentiators, or different trip types, but we did find, again, a really interesting technique and really interesting questions.